Hi everyone. The next topic is random variables. So probably you have studied random variables in either STAT 2010, 2210 or Math 5700, but we will have a quick review. A random variable is a map from a probability space to a set of numbers. So this is a little bit abstract. So this one example here. So think about flipping a coin twice. Probability space is this. So the first one is the first result, first flip result. And the second one is the second flip result. So this is head-head or head-tail or tail-head or tail-tail. So we have four possible cases. And we think about the total number of heads in this trial. So we denote this as X. Then if HH, the result is HH, the total number of heads is 2. HT, 1, TH, 1, TT, 0. So basically, the X connects each individual output to some number. So this is called random variable. So often we think about a distribution of random variable is this. Possible values are 0, 1, 2, and the probabilities are 1/4, 1/2, 1/4. And we don't really care about this so-called probability space, or in statistics, sample space. But original definition of random variable is that random variable is a map from some probability space to a set of numbers. We have the two kinds of random variables. One is discrete, the other is continuous. So first we discuss discrete random variables. A random variable is called discrete when the range of X is discrete. So if you're in mathematics department, you should know what is discrete. And if you are not, you need some definition of discrete. So discrete means each possible values are isolated, such as all integers. So for example, -2, -1. Excuse me, the 0, 1, 2, 3, and so on. So each possible outcomes are isolated. If this is a little bit vague for you, then you can think about just discrete random variables are countable. Actually, the countable and discrete are different concept, but for example, the all integers are countable and discrete. Okay, so now that we think about the probability mass function of a discrete random variable, for a discrete random variable X, the probability of X is equal to K is written as probability of X equal to K, P of X is equal to K, or lowercase p of K, or sometimes f of K. So K runs all possible values of X. If all possible values are 0, 1, 2, then K is 0, K is 1, and K is 2, 3 cases. And this function is called probability mass function. In the previous example, P of 0 is equal to 1/4, P of 1 is equal to 1/2, and P of 2 is equal to 1/4. So you can put it in a table or a histogram or just the formula I wrote down in the last page. And another example is continuous random variables. So continuous random variable is the random variable whose range is continuous. For example, the temperature, weight, height, age of people, and so on. So many physical variables are regarded as continuous variables. For continuous variable, we define a density function. So f of x, density function. So this is called a density function of x if this probability is equal to the area under the curve between A and B. So that means we have some curve, And if we have A and B, this area corresponds to probability. In this case, we say this curve f of x as a density function. So area under the curve that should be equal to 1 because by definition, probability sum up to 1. Okay, so cumulative distribution function for discrete random variable. So in the last page, we discussed the density function, but we now think about cumulative distribution function. So if we have density function here, we think about the probability that x is less than some value, for example, a, then this area is called capital F of A. So in this way that we define the cumulative distribution function. So cumulative distribution function, the first value, so the cumulative distribution function's value is the area, so that is between 0 and 1. So cumulative distribution function that start at 0, for example, if this point is, okay, say A0, then it starts with A0, then area becomes larger, then cumulative distribution gets larger faster, then like this. Okay, so cumulative distribution function, always the range is between 0 and 1. So the graph is between y is equal to 0 and 1, and it looks like this. So this is the graph of y is equal to f of x. So if you pick up the value a, then this value is f of a. So this is cumulative distribution function. So by definition, the derivative of capital F of x becomes the lowercase f of x. In our language, we have basically 4 functions for any random variable. So we have the d, p, q, and r. So d plus name, for example, for normal distribution, d norm is a mass or density function of f. So we discuss in the next page, but if we have a normal curve, then this height is d norm of x. And the second one is the p plus name, so p norm function, for example. This is cumulative distribution function, so capital F. So if we have a PDF, so this line is PDF, then p norm represents this. So if you are given x, then p norm of x gives this area. So in this case, probably 0.8 approximately. And the third one is q plus name, so q norm function, for example. So this is quantile function. So this is inverse of CDF. So that means if we are given alpha, then q norm of alpha is here. So given area, that we have just exactly one corresponding x value. So that is the q norm of x. And the fourth function is r plus name. So this is random number generated from this distribution. So if this is the density function, then random number typically ranges from -2 to 2. So if we type r norm of 10, we get random numbers between these two numbers. For example, negative 1.5, 0.2, positive 0.2, positive 0.7, negative 0.9, and so on. So this is our norm function. So basically, we have 4 functions for any distribution. So that is the code for random variables in R. From the next video, we discuss the more concrete examples of random variables.